Hello, today we are going to be talking about calculus. Alright, we've graduated from algebra, now we're moving on to calculus. And first off, we have to figure out what calculus really does. Calculus describes objects in motion. It describes things in a state of flux. It describes change. Algebra is very static. Algebra says here's a function, here are function values. We're going to talk about this function as it exists in this moment in time. Calculus says, hey, things in the real world are always changing. And calculus attempts to study those changes. Now there's a foundation that calculus is built upon. That foundation is called limits. All right? A limit describes a function's behavior and the y value that the function is approaching. Notice that it does not say what the function is. It talks about what the function is doing and where the function is going. It's about behavior and a y value that the function is approaching. Now, the first type of limit we're going to talk about is one that is kind of easy to wrap our minds around, okay? Convergent behavior. Convergent means converging, going together. So I have some curve here, I'm going to call it f of x. And I have this point in particular. All right, now we can talk about the behavior of this function as we kind of go along the curve approaching from the left. Now approaching from the left. And we can talk about it as we go along approaching from the right. Approaching from the right. And we see that as we come in, these arrows, they're going towards each other. They are converging, going towards each other. So we can talk about the limit of this function f of x, the limit, the behavior, where is it going? Now, x is still your independent variable. You plug in x values and get y values. So it's the limit as x approaches, and I have it right here, 3. The limit of f of x as x approaches 3. And we see as we approach x equals 3 from the left, as we approach x equals 3 from the right, these blue arrows are coming towards each other and they are converging towards this y value of 5. All right? So the limit of f of x as x approaches 3 is 5. Now that kind of makes sense, okay? Because this function, this smooth curve, it's continuous, it doesn't have any breaks in it, doesn't have any holes in it. It's what we call a well-behaved function. Well-behaved functions do what you expect them to do. So we expect this curve to be smooth. So let me change it up a little bit, okay? Let's make this a little more interesting. Let's get rid of that dot. And replace it with an open circle. So, this function is no longer well behaved. It is not continuous. We're going along, minding our own business. It bleeps out of existence for a moment, and then it continues back along doing what we expect it to do. Now here's the cool thing. This answer doesn't change. The limit of f of x as x approaches 3 is still 5 because this arrow is going up towards y equals 5. This arrow is going down towards y equals 5. The arrows are pointing towards each other. Now, does the function exist at x equals 3? No. There's an open circle. Of course, that function does not exist at x equals 3. But remember, a limit is not about what a function is. A limit describes behavior, what it's approaching. Okay? So, will this function ever equal 5? No. The function will never equal 5. It can get so close, it can go to 4.7, 4.8, 4.9, 4.91, 4.99, 4.999. It can get so close to 5, it'll never get to 5. It is the saddest story in mathematics. That function will get closer and closer and closer and closer to 5, but it will never, ever, ever get there. But that's okay, because limits are not about what a function is. It's about what a function is doing. The function is going towards 5. Will it ever get there? No. But if it did, if it somehow miraculously happened, based upon the behavior, it would go to 5. All right? So that's convergent behavior. As we come in from the left, as we come in from the right, we are approaching the same y value. Now, divergent behavior. This is where it gets cool, okay? I got the parent rational function, f of x equals 1 over x. Now, this is the graph that we know and love, okay? So, the limit of 1 over x as x approaches 0, and then this little negative sign where the exponent should be, that negative, that means where x approaches 0 from the left, okay? So, from the left. Now, we see that this function goes up, and it just keeps going up. It increases without bound. So, as we approach from the left, our y values go towards infinity. Now, will they ever get there? No. Infinity is not a number. You can't get there. But a limit is not about what a function is, it's about what a function is doing. We are going towards infinity. Now the limit of 1 over x as x approaches 0 from the right. Now that function is going down without bound. Negative infinity. Now infinity and negative infinity are not exactly the same thing. And we should be going towards the same value for us to have a limit. So we get different values. That does not exist. The limit as x approaches 0 does not exist. Now, let's think about what if we wanted to do the limit of 1 over x as x approaches 3? Well, sure. That function exists at 3 as you come in from the left, as you come in from the right. They approach the same value. All right, so this function has limits in infinitely many places. We just chose the one value where it doesn't because of that divergent behavior. Going up, going down, up and down are two different things. They're not approaching the same value. Over here, this is kind of a fun one. X minus 2 over the absolute value of x minus 2. I told you it'd be fun. Now this is what the graph looks like. We have this horizontal line, and then at 2, all of a sudden it just jumps up here instantaneously and then goes along its merry way. Now as we approach 2 from the left, the limit of f of x as x approaches 2 from the left, we're just kind of plugging along. It's a horizontal line, and the y value that we're trending towards is negative 1. Now the limit of f of x as x approaches 2 from the right, as we come along, we're approaching positive 1. So here's the thing, we have y values. That's kind of cool. In the last example, we didn't. Here we do, but the y values are not the same. So that limit does not exist either. All right? Now remember, it's not about what the function is, it's about what it's approaching. Okay? So convergent, approaching the same y value, divergent, approaching different y values. Convergent, the limit exists. Divergent, the limit does not exist. So up here, you need to give me a numeric answer. Down here, does not exist because you're coming from left and right. Two different things. All right, it's not working. So here's the cool thing about calculus, okay? In this problem, we're approaching x equals 0. You plug 0 into the denominator. Algebra, that does not work. Cannot divide by 0. A lot of you in Honors Trig wrote a proof about that. Can't divide by 0. Over here, same thing. We're approaching 2. Plugging 0 into the denominator. Does not work. Well, here's the cool thing about calculus. Calculus, you can divide by 0. All right? That's how cool calculus is. It takes algebra, and where algebra stops and doesn't work anymore, calculus is like, boom, we're going to divide by 0. Okay? So I want to show you some ways that we do that. Don't want to pull a nail out of the wall. Aha! So evaluating limits. Now there's kind of 4 main methods that we're going to look at, okay? The first, direct substitution. And you really want to go through it in this order, okay? Now, a lot of these problems, they are written so that you can do one of these methods, okay? So the first is direct substitution. When you have a function that is well behaved, you have a quadratic, okay? That's a parabola. And it kind of does what you expect it to do. It comes down, it bottoms out at the vertex, and it goes back up. Okay, every quadratic does that. It's that parabola shape, it goes down or it goes up. Okay? So this function is well behaved. It's continuous. It exists everywhere. There are no surprises with a quadratic, which means you can do direct substitution. Just go ahead and plug in 5. So 3, 5 squared, plus 1. 5 squared is 25. 25 times 3 is 75. And you get 76. Very cool. You always want to try direct substitution first because it's the easiest method. So let's look down here. The limit as x approaches -6 of this quadratic over this linear. Now you try direct substitution first. See what happens. Mostly, plug it into the denominator. -6 plus 6, 0. That's no good. You cannot divide by 0. So this function has a discontinuity. There's somewhere in that function where things don't quite work out the way you expect it to. So here's what we can do. Look at the numerator. You see a quadratic. Now when you see a quadratic, if you're anything like me, you're like, oh man, I need to factor that. I need to get 2 sets of parentheses, 2 numbers that multiply to the last number but add to the middle number. If you're anything like me, that's what you think whenever you see a quadratic. So 2 numbers that multiply to 18 but add to 9, that is going to be 6 and 3. Now this is called the factoring method because you're going to factor the numerator or denominator down, and then this x plus 6, that's what I like to call the problem factor. That's what's keeping you from direct substitution. Well, now we have a copy of that x plus 6 in the top, and you can do the most satisfying move in mathematics, the cancel out ninja swipe. Boom! All you are left with now is x plus 3. X plus 3 is a linear function. Linear functions are well behaved. They kind of do what they're supposed to do. There are no surprises. So you plug in that -6. And you end up with an answer of -3. That is the limit. That is the behavior. That is what the function is approaching. Now, will this function ever equal -3? No. It won't work. There's a hole in the function at x equals -6. It won't work. But hypothetically, theoretically, if we could plug in -6, we would expect that answer. Because that's what the function is going towards, that convergent behavior. As we get closer to x equals -6, the y values get closer and closer to -3. Now, this original function, will the original function ever equal -3? No. But if it could, and that's what calculus looks at. It looks at that possibility. What are we going towards? Yeah, we're not there. We might never get there. But if we did get there, this is what we can expect. Okay? The next one, rationalizing. Rationalizing, if you see square roots being added or subtracted, you know this is going to be a rationalizing problem. Okay? Now you try direct substitution. You always want to try that first. Plug 0 in for x, you get 0 in the denominator. That doesn't work, okay? So what we're going to do is we're going to multiply by the conjugate pair, of the numerator. The conjugate pair means take this minus and make it a plus. If it was a plus, make it a minus. So we're going to multiply by root x plus 3 plus root 3. And we don't want to change the value of this function, we just want to change what it looks like. So we're going to multiply top and bottom by the same thing. Going to make a real big fraction bar here because we're going to FOIL the top and bottom together. So root x plus 3 times root x plus 3, that is root x plus 3 squared. Root x plus 3 times a positive root 3, that is plus root x plus 3 root 3. Negative root 3 times root x plus 3, that is minus root x plus 3 root 3, and then negative root 3 times a positive root 3, that is negative root 3 squared. And in the denominator, I'm going to leave it all separate, okay? I'm going to leave that x out in front by itself, and then the conjugate pair, I'm going to leave that in parentheses as well. Because remember, I talked about the problem factor. You want to get rid of the problem factor. We want to get rid of this x. So why would we have x get all tangled up in this? Let's leave it out in front so we can factor it out easily. All right. Now, for those of you who, like, if you go to a playground, okay, the bigger the slide, the more fun it is. If you like simplifying algebraic expressions, then this right here is the biggest slide on the playground, okay? We have a square root being squared. That cancels out. We have another square root being squared. That cancels out. We have the root x plus 3 root 3. We have a negative root x plus 3 plus 3. The positive and the negative. Those cancel out. So what we're left with, stay with me here, all we're left with is x plus 3 minus 3. The plus 3 and the minus 3. Those cancel out. So now all we have in the top is just this tiny x all by itself. And look at that. There's a tiny x all by itself in the denominator as well. So the x and the x cancel out. And we are left with the limit as x approaches 0 of 1 over root x plus 3 plus root 3. So now we do our direct substitution. Go ahead and plug 0 in for x. We have root 3 plus root 3, more commonly known as 2 root 3. So this function does not exist at x equals 0. But if it did, that would be your answer. All right? So direct substitution, factoring, rationalizing. If all else fails, we're going to be 21st century citizens and look at technology. Most importantly, a table of values. So I plugged that function into my calculator, e to the x minus 1 over x. I look at a graph and I say, hey, that looks pretty continuous. Looks like an exponential function. So then I'm going to go to my table setup. All right, we're going to start at x equals 0, delta table of 1. So I second table, and I look here and I say, at x equals 0, it's an error, which makes sense because this doesn't exist at 0. And to the left and the right, I see different numbers. Well, here's the thing. This is called local linearity. We're going to zoom in on that graph as much as possible. So I'm going to go back to my table set, and I'm going to start my table at 0, and then I'm going to make this delta table, make the steps a lot smaller. So 0.001. And look at that. Now to the left, negative 0.001 is 0.9995. To the right, 0.001 is 1.0005. We're getting close. As we come in from the left, we're coming up towards y equals 1. So coming from the right, we're going down. So what I'm going to do is I'm going to zoom in a little bit more. Start my table at 0, 0.00001. 4 zeros and a 1. And look at what that calculator does. That calculator starts rounding and says, hey, as you get closer to 0, it does not exist. But if it did exist, from the left and the right, we're approaching 1. So, limits. It's not about what a function is, it's about what a function is approaching. So, can you divide by 0? No. But calculus is all like, hey, if you could, these are the answers you would get.